Okay, I want to do a little demo of JMSL's MusicJob. MusicJob is a class that executes some piece of program code on a timeline. It goes to sleep, wakes up, does whatever you programmed it to do, goes to sleep some amount of time, wakes up, does whatever you programmed it to do, and so on. And it repeats that some number of times. The number of repeats is programmable, and the amount of time between repeats is, of course, programmable. And it's a root class that lets the computer music programmer specify algorithms that happen on a timeline. Looking at our Eclipse project here, we go to Properties, and we want to make sure that the Java build path has jmsl.jar in its class path. Okay. Then I'm going to declare a new class. I'm going to call this MusicJob Demo. And I'm going to increase the font size a little bit. MusicJob Demo extends MusicJob. It doesn't know what MusicJob is, but it will once I let Eclipse import MusicJob. All right. The class that the method in MusicJob that you can override to execute whatever you want it to do every time it wakes up during one of these repeats is not coincidentally called repeat. Repeat takes in a playtime. This is a mathematically correct timestamp that is independent of any kind of scheduling jitter. And it returns an updated playtime to reflect how long you want this MusicJob to go to sleep. So if the playtime comes in and it does something, then the playtime going out is going to be something like playtime plus, let's say, half a second. So the JMSL scheduler will call this MusicJob's repeat method numerous times, as many times as the MusicJob's set repeats is set to. And every time it repeats, it will go to sleep for a half a second. Let's have it print something out every time it repeats. I'm going to have it print its name. I'm going to have it print get its repeat count. Let's have it print the playtime. And let's have it print out the actual wall clock time, because that's going to be an interesting thing to look at. Okay. That's enough for us to actually give this a try. I'm going to go create a main method. Typed in MAIN, then I hit Control Space, let Eclipse complete that method signature for me. I'm going to say MusicJob Demo equals new MusicJob Demo. I'm going to say MusicJob Demo dot set repeats. Let's say 4. And then I'm going to say MusicJob Demo dot launch. Launch requires a timestamp. So JMSL has a static method called now, which consults the system clock. and adds a little something called advance time, which we'll illustrate in just a second. Okay, let's run this. Okay, so the name of this thing is called MusicJob 0. Every time you create a music job, that index gets incremented, so they have distinct names. This is the repeat count, the 0th, 1st, 2nd, and 3rd time that it executed. It shows you the timestamp that it receives. The play time is equal to this value. This is one of the vagaries of computer math, right? Of course, a number this small is imperceptible. So you see that the pure timestamp increments by exactly 0.5 seconds as promised up here. And again, just ignore this. This is just how math works. Real math is not the same as computer math, right? Those numbers, those don't map exactly. All right. Look at this, though. The wall clock time is 0.016 seconds after JMSL initialized. And then this is not, it's a little more than a half a second later, right? These wall clock times do not go up exactly 0.5 seconds at a time because threads are a little bit jittery, right? Scheduling on a computer is not precise. However, if you maintain a mathematically perfect timestamp, and if you call a music API like JSON, which has an independent sort of interrupt level thread running, you can post things a little bit in the future with this timestamp, and you'll be assured that the music that you are actually scheduling is not jittering. It's like a messenger showing up a little bit early and saying, you know, ring a bell at noon, and then the messenger runs to another appointment, arrives a little bit before 1 o'clock and says, ring a bell at 1 o'clock. That messenger could show up 5 minutes early or 3 seconds early, but as long as they arrive early and present the exact timestamp of when you want to ring that bell, the audience will perceive the bell ringing exactly at noon and exactly at 1 o'clock. All right. Well, I want to bring your attention to something else. The playtime here, 0.015, is actually in the past compared to the real time. So all of these would actually be late. The messenger is actually late in every single one of these cases. The real time is 1.017 seconds, and the intended playtime is 1.015 seconds. That's in the past, so that's not going to work. That's why JMSL has this notion of advance time. So I'm going to set the advance time to, let's say, 1/10 of a second. That means it's like setting your alarm clock a little bit early. It's like setting your home clock a little bit early. You think it's noon, but it's really a little bit afternoon, so you get out the door early and you arrive at all your appointments on time or a little bit early. So we're going to run this again and see the difference. So again, the difference between these timestamps are exactly 0.5, ignoring this rounding error. But notice that all of these are actually in the future of the real time. This is the real time, 0.512 and 1.008. But all of these are ahead of time. So in this case, this messenger, the playtime messenger, is actually arriving early. It arrives at 0.512 seconds, and it can schedule a musical event for 0.609 seconds, which is in the future. Arrives at 1.008, schedules something at 1.109. Arrives at 1.513, schedules at 1.609. So all of these things will go off on time.